Welcome everyone to this to another ZX seminar. Today we have Maximilian Rüsch, who will be talking to us about this new result on the completeness for fault equivalence of Clifford ZX diagrams. So please, Maximilian, if you want to get started.
Yeah. All right. Thanks. Yeah, as you said, I'm Max. This is a talk about my master's thesis, which I did in Oxford, and the follow-up work to develop this thesis into an archive paper. And this work was done, the follow-up work was done with Ben and Alex. And it's on the topic of, as you said, completeness for fault equivalence of Clifford ZX diagrams. And I explain kind of what each of those bits mean as we go along. So in this sort of group, we know what the ZX calculus is. I will just shortly explain what I mean with the ZX calculus here, what sort of ZX calculus I'm using. I'm using the Clifford fragment of the ZX calculus, which just has the pi over 2 phases on the spiders and uses these 8 rules. And this Clifford fragment has 2 key properties. One of them is soundness, such that when you derive something using these rewrite rules, then the property actually holds. So these 8 rewrite rules that we have here, they give you semantic equivalences. Whenever you have 2 diagrams and you have a rewrite rule between them, then you are asserting that these 2 diagrams kind of implement the same linear map. So with soundness, if you derive some rewrite using these rewrite rules, then you're guaranteed that the property actually holds. And then there's completeness, which basically does this the other way around, that if you have some property, some semantic equivalence that holds, then there exists some rewrite sequence from one diagram to the other. So this is fine as it is. The ZX calculus, however, has some shortcomings if you just look at the semantic equivalence. And the main one is that the arbitrary application of these rules doesn't necessarily preserve the diagram's behavior under noise. This is a thing that was sort of addressed in the paper introducing fault equivalence by Ben, Alex, and Baldassar. And their notion of fault equivalence is something that replaces this semantic equivalence, or like kind of strengthens it in a way that it relates less diagrams. And now these diagrams should be under some notion of faults and noise, and under some notion of being equivalent enough, should be equivalent under noise. So these are rewrites that capture and preserve the diagram's behavior under noise. And just to give you a quick motivation about what you can do with this, for example, what you can do is you can derive more efficient syndrome extraction methods. This is an extract from a recent paper from the same authors, where they derive a new method of doing Steen syndrome extraction. And then they go on to show using simulations that this Steen syndrome extraction actually performs better in this case because it uses fewer ancillas and similar metrics. And to have a full introduction into the fault equivalence and sort of a more rigorous motivation, I encourage you to look at the following 2 talks, one from the ZX seminar and one given at the Topos Institute. I'll be constructing fault equivalence from the ground up, so we're all up to speed. I will first like to clarify what I even mean by a fault. In this case, I just want to say that a fault is something that's a product of Pauli's on diagram edges. So we have a bunch of diagram edges where on each edge we can place some single Pauli, and a product of those Paulis is like one atomic unit that we call a fault. This is something that can go either wrong or it doesn't. In which case, if it goes wrong, then we place the indicated Paulis on those edges, and if it doesn't go wrong, then we don't. Then we just write it identity everywhere. So a fault for a diagram D with edges E is something in the Pauli group to the number of edges. And then I will denote the effect of a fault, so the diagram that we obtain when we actually instantiate the fault on the diagram, I will just denote it by d to the f, if f is the fault. And now what we can also do is assign some expression of likelihood or unlikelihood in this case by assigning a weight to the fault. This may be familiar to you if you're used to Pauli weight, but basically the higher the weight of the fault, the less likely it is in our model. This leads me to defining what a noise model is, or what we consider a noise model. A noise model is a set of faults that are like the independent error mechanisms of things that can go wrong. So this is what we call the atomic faults. And then the noise model is just a map from these atomic faults to a weight. So it assigns each of these atomic faults a weight, which we call the atomic weight. The set of all faults is just a group generated by this atomic fault set. And now a thing we can do is not only assign a weight to these atomic faults, but we can also assign a weight to the generated faults. This is something called the induced weight. So for each noise model, you can uniquely induce a weight function, which is given by this expression. And this looks like sort of slightly weird to parse at the first sight. But what's basically saying is that the induced weight is the cost of the cheapest way to construct the given fault. So for each decomposition of this fault into atomic faults, if I take the sum of atomic weights of the decomposition, then the cheapest way to construct this is the induced weight. One example is, for example, if I have this edge where I have three Paulis, x, z, and y, and x and z are both able to be constructed with the atomic weight 1, and y is constructible with atomic weight 3, then y, of course, by definition, has the atomic weight 3, but because I can construct it using one x and one z, which their sum is weight 2, it has the induced weight 2. So the induced weight can in general be lower than the atomic weight. One simple example of a noise model is edge flip noise. And just for some arbitrary diagram, what we can do with edge flip noise is basically it limits the Paulis that can exist in a noise model to being Paulis that only flip one single edge. So since they act locally on one single edge, we can annotate their weight on these edges and sort of make the noise model visible on the diagram itself. This is sort of similar to annotating something in the source of your program code rather than somewhere else. So we can do this using these triples for the weight of the x, y, and z faults. And we can use the dash to say that we want to emit an atomic fault from a noise model. We will handle these sort of edge flip noise models a lot, but we want to introduce some sort of quality of life because adding these vectors to every edge is sort of unwieldy. So the first quality of life that we're going to introduce is an abbreviation for having this sort of triple of dashes, so no atomic faults on an edge. We do this by marking these edges purple, and this is what might be known to some of you as idealized edges. So there are no atomic faults on this edge. And then whenever we have one single atomic fault on an edge that is a z fault, then we will abbreviate this triple dash dash weight just with the weight, just with the number. This is because we will handle lots of just single z faults on edges in this talk. Now, one additional ingredient that we will need is defining when a fault is detectable. And I will just put this out here and say that a fault is detectable if its effect is 0. So if instantiating the fault on a diagram kind of makes the diagram go to 0. And to make this sort of interesting in the talk, we will assume that the base diagram is just non-zero, because if the base diagram is 0 itself, then this whole talk won't really make sense. So we'll assume that it's non-zero. And now we're ready to define what fault equivalence is on two diagrams. So I said it's strengthening semantic equivalence, and indeed semantic equivalence is one of the like prerequisites for fault equivalence. So if you have two semantically equivalent diagrams with their respective noise models, then the first diagram under the first noise model is fault equivalent to the second diagram under the second noise model if for every fault that's generated by the first one, it's either detectable, in which case, because we're post-selecting on diagrams, we don't really care about it right now. And if it's not if it's not detectable, then there must exist some other fault on the second diagram that has the same effect and that has at most the same weight. So it's at least as likely as the first fault. And we require not only this direction, but we also require the other direction, the symmetric condition. And we will write this sort of with the equal sign with the little hat on it. One thing that we can read from this definition immediately is that the fault equivalence only cares about the undetectable faults. So if we have any detectable faults in our noise model that are generated, we can immediately discard them. At least for checking fault equivalence. And it only cares about these undetectable faults up to equivalence classes. So the equivalence classes are sort of these faults, these equivalence classes under the effect of the fault. So if I have two faults that are generated by the first noise model that have the same effect, and where one has higher weight, and I have another fault generated by the second noise model that's sort of like the corresponding one for the one with lower weight, the one that has the same effect and the one that has a lower weight than the first one. Then I immediately have a corresponding fault for the second fault from the first noise model. So it only cares about these faults up to equivalence classes, and we only really need to check the minimum weight fault in each equivalence class. We can reword this to say that two diagrams that are semantically equivalent are fault equivalent if and only if each of those pairs of equivalence classes that we can pair up has an equal minimum weight. So
I have a question, Max.
yes,
So, when you're talking about minimum weight, you're thinking in the context of the induced weight that you introduced earlier, right?
yes, yes. You can see my pointer?
Yeah,
Yeah. So these weight functions here are indeed the induced weight functions, not the atomic ones.
thanks.
All right. And so, for example, these are four fault equivalent rewrites that are introduced in the fault equivalence paper or the paper that introduces fault equivalence itself. I'm not going to be using those as some sort of set of rewrites that I'm trying to prove complete. I'm going to be using this set, which is a large set. And we can divide it sort of into three regions. The first region is the Clifford ZX axioms, so the ones that we were using in the semantic equivalence as well. And this time they're in the fault-free regime, so all edges are idealized. Then there's another region which sort of introduces basic handling of faults and allows us to ignore phases of faults and ignore relative phases that could be introduced when commuting two faults on diagram edges. And then there's a third region which allows us to swap out the atomic faults of a noise model without actually changing the equivalence classes of the noise model. And we will see how that works later. Of course, you can prove that this set is sound, and you will have to trust me on this, or go and read the paper. Because I'm like this talk is only concerned with completeness. So if you're here for completeness, just continue listening.
Max, can I ask if you go to the previous slide from this one? So here you just say these diagrams are fault equivalent without any weights or anything. Are you sort of saying regardless of the error model that you choose, these will always be fault equivalent?
So in this case, these were proven fault equivalent for just single for edge flip noise where every edge flip has weight 1. So sort of one of the simplest noise models.
Okay.
I'm unsure whether you can make more general statements than this.
Right. Thanks.
All right. So the proof of completeness is going to commence as follows. So usually when you want to prove some completeness axiom, either like you have two options. Either you reduce your statement to another completeness result. You try to express some of your axioms in terms of other axioms that are complete. In this case, we don't have this option since there are no other results for fault equivalence. This is the first one. And so the other option that we have is to find and reduce our diagrams to some unique representative per class of relations or of the relation between diagrams. And this is what we're going to try and do. And it's going to commence in roughly 2 stages. First, like as a preparatory stage, we will have to express the noise model on the diagram itself in a way that's sort of more rigorous than this edge flip annotation, and in a way that also works for not just edge flip noise models. And then we're going to separate this description of the noise model from the base diagram itself, the diagram D, in a way that leaves the diagram D as completely fault-free. And then we have 2 distinct parts that we can normalize or uniquify on their own. And then when we have 2 unique parts and we put them together, then we put them together in a unique way, then we receive another unique thing. And since we can reproduce this whole procedure diagrammatically, suddenly we have completeness of the axioms. So let's get on with the first stage, separating the description of the noise model from the diagram. And I'm going to be using one relatively simple running example. It's this fault equivalent rewrite, which sort of expands or contracts, depending on which way you see it, one single green spider into a rectangle of green spiders. And I'm going to be using this just using X edge flips, all equally weighted with 1. We could also look at Z flips, but since all spiders are green, these are not really interesting here. And Y flips can be thought of in terms of X and Z flips, so we're just going to be concerned with X flips here. And for the entire first stage, we're just going to look at the right-hand side of the diagram, since it's more interesting, and we can reproduce everything that we do to the right side to the left-hand side as well. So the first question that we have to answer is, how do we even represent these faults diagrammatically? And sort of a simpler question is, how do we represent Pauli's diagrammatically? One option would be to use Pauli boxes, which are sort of a controlled version of a Pauli. And basically, whenever you top these with a green spider that either has 0 or a pi phase, then you're toggling on or toggling off whether this Pauli box introduces a fault of the corresponding type on this edge. And through this, we can define something that we call a fault gadget. So for some fault over here, some product of Pauli's, we can introduce these Pauli's as Pauli boxes and then connect them up using a red spider. And everything else in here is fault-free. And the only thing where we're going to allow to introduce the actual fault that's going to have the effect that we want is this edge right here. And now we can assign to this fault the atomic weight of whatever atomic weight this atomic fault had in our noise model to be able to to faithfully represent it. And one thing we're going to do is, since identity boxes correspond to these just free-floating red spiders, we're going to merge in the free-floating red spiders and just not draw the identity boxes. And so one side result that is sort of interesting here is that we have now used just this edge flip noise annotation to be able to express an arbitrary product of Pauli's. So one side result from this paper is that the edge flip noise is indeed universal for all weighted Pauli noise models. There's a question.
Yes. So suppose that you have this atomic weight for the leftmost diagram, where Z has weight 2, X has weight 1, and Y has weight 3. Then how would you calculate the edge weight of the edge flip on this edge in the middle?
So what we're going to do, and we're going to see this with the example diagram in a few slides, is for each atomic fault, we're going to have a separate fault gadget. And so the separate fault gadget then exactly carries the atomic weight of the fault.
In this case, it would be 3 plus 2 plus 1, which is 6.
You wouldn't form a sum, you wouldn't add it. You would add 3 very distinct fault gadgets that have just their own annotations. This will become clear in a few slides, but perhaps if we wait a couple of slides and we can clarify this.
So sorry, my main question is, how do you get this 5 for this edge flip in the dongles?
This is just arbitrarily chosen. So the noise, the way we model noise, we allow the sort of user of the noise model to specify for each atomic fault an completely independent weight and completely independent integer that specifies the likelihood or unlikelihood of this fault.
So in this particular example, there's one single atomic fault that happens to have weight 5, which we represent with this one atomic.
Oh, so you're saying that because this is a coherent fault, so every flip on each wire has the same weight. So that's why you have this 5 on this dongle edge.
This is not edge flip noise. This is like a single fault, which happens to be represented by 3 Paulis in this particular case.
Oh.
So this is like say that you do a Toffoli gate and you have 3 errors happening simultaneously. That's like what this represents.
Yeah. One advantage of Pauli gadgets is to make sort of more complicated atomic faults really visible in the diagram. Because over here, you could perhaps say that these faults could be independent, but if we want to express them as one single atomic fault, then we just package them in this as this fault gadget, like sort of actually bundle them together via diagram matches.
Thank you.
Right. So we now want to perhaps verify whether the fault gadgets actually do what we want them to do. And if no, in the case that no fault happens, we can just use the ZX calculus to show that a fault gadget just reduces to the linear map, to the identity linear map. So it does nothing to the diagram. And if a fault happens, then we can also use the ZX calculus to show that the Z fault over here that we allow on the fault gadget propagates out to have the same effect as the original fault that we wanted to have. And then we are left with an empty fault gadget, which we can again reduce to the identity linear map. So the fault gadget does what we want, and in both cases, whether there's no fault happening or there is a fault happening, faithfully represents this atomic fault. Now, in the running example for this only X edge flip noise, we would instantiate this noise like this noise on the diagram like this, where we have for each edge flip have a separate fault gadget with just the weight annotation. Now we have defined how we diagrammatically represent noise, how we diagrammatically represent these atomic faults. And now perhaps you might wonder, well, what can we do with these fault gadgets? Is there anything that we cannot do? What are the restrictions? And so the first thing that we may realize about Pauli boxes is that they are basically just a Clifford conjugation of a single green spider that's connected to this diagram edge. So for the Z, this would be the identity Clifford, and then for the X, this would be the Hadamard, which is self-adjoint, and then for the Y, this would be a red pi over 2 spider. And the for the purposes of being sort of a representative of a fault, so for the purpose of being capped with either a green 0 phase or a green pi phase spider, the Y box actually has two implementations. It has this one, and then the mirrored version where we put the minus phase over here and it's sort of the plus phase over here. And then we're going to see how to derive this later. Using this Clifford decomposition, we can already show that if we have two Pauli boxes that are attached to the same gadget on the same edge of the same type, then these two cancel out. So we can decompose them into the Clifford and the adjoint, contract the Clifford and the adjoint to the identity, apply fusion, apply the Hopf rule, and then contract again. And then we're left with just a dangling identity Pauli box, which we can contract into the red spider of the fault gadget. But we can do more complicated things. We can, for example, show that a Y box can be composed from an X and a Z box if you allow to ignore some phase. So that's equivalent to stating that a Pauli Y is equivalent to a Pauli X and a Pauli Z up to some phase. And here we're using this sort of like one of these phase ignoring axioms that we've introduced. Now, as I said, we can show that we can mirror the Pauli Y box implementation, again using this phase ignoring rule. And then using these two together, we can show that if we have two X and Z boxes attached to the same gadget on the same edge, then we can commute them past each other. We can compose them into a Pauli Y, mirror its implementation, and decompose them again. Now, you might be wondering, well, these are for X and Z boxes attached to the same gadget. What about different gadgets? You can show this too. This works as well. And then you're using another phase axiom, which can remove relative phases between different gadgets. And this sort of just means that in essence, gadgets behave exactly the same as Pauli faults, at least for the Pauli boxes on the same edge. So what if now we want to transform these two fault gadgets into each other? Because in some way they're equivalent. Say, for example, you have this diagram which is representing a C0, and you have one X fault in front of the control, then this X fault in front of the control should be equivalent to two X's after the C0. So ideally, what we want to do is to transform gadgets into all other equivalent gadgets. So one question is, what even do I mean by equivalence here? Is this equivalence just this effect equivalence that we use in the definition of fault equivalence? I'm saying equivalence a lot here, but just bear with me. So we're gonna try and define this equivalence. The first idea that we had just now was that two faults on the diagram are equivalent if they have the same effect. And this turns out to work and be sufficient for undetectable faults. But it turns out way too coarse for detectable faults. If we recall, the detectable faults are faults such that their effect is 0, then suddenly under this notion, all detectable faults are equivalent. Now, an example to see where this doesn't work out is if we have these two detectable faults in our diagram. If we imagine our diagram to be consisting of two ZZ checks, then any fault that happens between them changes the parity of those ZZ checks, and then thus makes the fault detectable because suddenly we're not getting the expected parity outcome between those ZZ measurements anymore. So these two faults are detectable, and now we have their combination, which if we instantiate both of them and then push them outside to the boundary, this is suddenly a non-trivial combination. So these two faults are not equivalent in two senses. One, if we use both of them, they have a non-trivial combination. And two, if we actually try to use the ZX calculus rules to convert one into the other, we will find that we can never actually exactly obtain this diagram from this diagram, or the other way around. So these two faults are just not equivalent in the sense that we want them to be. So we tried to come up with another idea. If we recall the C0 example, then we realize that the faults that we want to consider equivalent, this x in front of the control and this xx after the C0, they actually form a stabilizer of this diagram. And we can say that this stabilizer is actually just another fault. It's just a product of Pauli's. And it's one of a special class called the inconsequential faults. We will define an inconsequential fault just to be a fault that does nothing to the diagram. It doesn't change the diagram. So indeed, every stabilizer, almost by definition, is an inconsequential fault. And now the next idea that we're going to have is that if we have two faults on the diagram, then they're equivalent if there exists an inconsequential fault such that this inconsequential fault relates them in a way. Yes. Question.
Hi. Is there any reference to a quantum code of some form when you say faults are equivalent, or is it more so on a diagram level?
It's on a diagram level. So
I guess traditionally when you talk about faults and sort of degenerate errors and all that, it's always reference to a particular code, right? For example, I was wondering what other connections. Can you just construct a code from some set diagram, for example? Is that a good way to reason?
So here we're sort of on a subcode level where there's no canonical code here. We're not in the environment of some code in the general case. And this equivalence is just in terms of how can we push around these products of Pauli such that they are that they look the same. So it's I don't know if that exactly answers your question, but
if I like so I mean fault equivalence is really taking a circuit-centric view. It's really looking at the circuits. And one way to think about these inconsequential faults, I'm not sure if you've heard the term of gauges, like in a circuit. So it's really literally if you have a C naught, it's exactly the fault that we have above. If you want to construct a code out of all of this, you can go kind of down the route of like Delphos and so on, of like building these space-time codes. And then like you can build for each diagram, you could build a subsystem code. And then these inconsequential faults are exactly also kind of the gauges, like the stabilizers of that subsystem code.
Okay.
But in this case, I think we're just taking a circuit-centric perspective, and it basically boils down to you can have a circuit where a lot of faults happen, but somehow they happen to propagate in such a way that they cancel each other out.
Okay, so it's essentially I can think about it as this space-time code by Delphos and others.
That's definitely, yeah, you can definitely define space-time codes on ZX diagrams just the same way you would on circuits, yeah.
Okay, all right. Thank you.
We're talking a lot about space-time here, which is fitting because we're gonna end up accepting this idea and we're gonna calling it space-time equivalence. So two faults on a diagram are now space-time equivalent if there exists an inconsequential fault that relates them. And this turns out to be exactly what we need to transform fault gadgets from one into the other. And we're going to see this by having a derived rule that allows us to introduce inconsequential faults into our fault gadgets. So if we have some base diagram D, which can be just some partial subdiagram of the like bigger context diagram that we operate in currently, and we have some fault gadget, then what we can do is if these Pauli boxes, if this product of Pauli's is a stabilizer of the diagram, we can just for free introduce it into the to the fault gadget. So we can multiply this fault gadget with some inconsequential fault. And then using the cancellation rule, where we cancel all the same Pauli boxes on the edges, we can now transform fault gadgets into space-time equivalent gadgets. So if we have this sort of junction green spider here, then one X in front of the in front of this junction, we can introduce the local stabilizer of this diagram to the fault gadget, and then cancel out these two duplicate boxes, and then be left with the fault gadget that represents a fault that you would not usually obtain just by pushing the pi through this spider. Now, one question we may want to answer, and that we will indeed need, is how can we efficiently determine whether two faults or two fault gadgets are actually equivalent? And for this, we want to dive a bit deeper into inconsequential faults. One thing we do realize is that local spider stabilizers are inconsequential. So if I just look at one part of my diagram, one single spider, then locally, if I have some Pauli product that's a stabilizer of that spider, then this forms an inconsequential fault. This is sort of a almost trivial statement. And the product of two inconsequential faults is again an inconsequential fault. But what's not a trivial statement is that this group of inconsequential faults for a diagram is exactly the same as the group of faults that are generated by those local spider stabilizers. Eventually, we can combine these spider stabilizers and these inconsequential faults into just full stabilizers of the diagram. But to some of you, this might sound kind of familiar, these like local rules that compose into stabilizers. This is basically just a notion of Pauli webs. So Pauli webs, for those where that's new, are basically a method of making a Pauli product visible on a diagram. So for each diagram edge, you can annotate it with a highlighting corresponding to whether an X and a Z Pauli is sort of active on this diagram edge or participating in the product. So, for example, this highlighting would describe a valid stabilizer for this diagram and its internal routing inside the diagram. So how you would push a sort of one Y fault over here through the diagram to obtain a ZZZ fault over here. And so I will define a Pauli web to be a Pauli product such that for each spider in the diagram, the restriction of this Pauli product to the spider or to the adjacent edges of the spider gives you a stabilizer of that spider. These Pauli webs come in two flavors. One is the stabilizing Pauli webs that highlight some boundary edge, and one are the detecting regions or the detecting Pauli webs that highlight no boundary edge. And we'll see why they're called the detecting ones in a second. For this, we need some new notion that is called firing the Pauli webs. So we say that we fire a Pauli web when we introduce, for each of the spiders in the diagram, we introduce the Paulis that are sort of dictated by this Pauli web for introduce each spider stabilizer according to this Pauli web, and then we merge all the Paulis that we just introduced on all the internal edges. This procedure may give you a global phase sign that we cannot ignore. So we kind of have to annotate Pauli webs with a sign. And so an example of this would be, for example, this detecting region. If we return to our running example, we have these two checks that where we can use their parity to sort of detect faults in between them. And indeed, these two checks form a detecting region. So this is a valid Pauli web. And then if a fault occurs between those two checks, if a fault occurs that anti-commutes with this detecting region, then if we try to fire this web and then merge all the internal Paulis, because we have to commute one green and one red pi, we obtain a global phase of -1. And then suddenly we're back to the original diagram, but just with a phase of -1. This, however, gives us the relationship d equals -d, and this can only be true if d is equal to 0. So if the diagram with the fault is 0, which makes the fault detectable. And so not only do we have to care about these signs, but they're like really vital in us determining what, like defining or like making sense of a detecting region in itself. They are, however, useful for much more than just detecting regions. So we can now look at the interaction between Pauli webs and faults beyond detecting regions. If we recall that Clifford diagrams are just completely described by stabilizers, then what we can do is we can realize that all that faults do to Pauli webs and in turn stabilizers and detecting regions is just flip their sign, but they may not change their routing through the diagram. So, for example, if I have this green Z flip over here, then its interaction with the green Pauli web is just nothing. And its interaction with the red Pauli web is exactly the same routing, but just with a phase of -1. For undetectable faults, the diagram with the fault is also fully described by stabilizers. Do you realize, like you recall, it's undetectable, so the diagram is non-zero. And so it can also be fully described by stabilizers. And since all the undetectable fault may do is flip the sign, we can sort of map the original stabilizers to the new stabilizers via their boundary conditions and obtain a difference in these Pauli web signs. So suddenly we can fully describe an undetectable fault by the sort of sign changes of stabilizing webs. The detectable faults essentially do the same thing, except because they're detectable, they flip at least one detecting region, because otherwise they would be undetectable. So we conclude that we can now express all faults through changed signs of Pauli webs. How is this useful? Well, you can already sort of guess from the way that Pauli webs are constructed similarly to space-time equivalents, but you can prove that indeed two faults on a diagram D are space-time equivalent if and only if they flip the same Pauli webs. And you can go further, and because for undetectable faults for non-zero diagrams, you can completely describe them by stabilizers. This means that two undetectable faults are space-time equivalent if and only if their effect is the same. For detectable faults, because two space-time equivalent detectable faults must flip the same Pauli webs, this sort of means that just using space-time equivalence, you can never escape like you can never change whether a fault is actually detectable or not, and you can also not change in which which detecting regions it's caught in. So this sort of handling is nice, but the detectable faults still stay detectable, and so the gadgets used to represent those faults are stuck in the detecting regions. We do not yet obtain the separation that we wanted for this entire first stage to happen. To solve this sort of remaining problem, we introduce a thing called flip operators. So for any given basis of detecting regions, we introduce something called a flip operator collection, and that's a set, such that for each basis element for detecting regions, there is some unique operator, some Pauli operator that anti-commutes exactly with that basis element in the context of the basis. For our running example, we have one detecting region, so our basis is one element. And then we can choose any one of those faults over here, and indeed anything that anti-commutes with the detecting region. It doesn't have to be one of those three, to be our valid flip operator. And we can also combine these flip operators like oddly many of those flip operators to form another valid flip operator. One thing that you can prove again is that you can efficiently obtain a collection for any diagram D, efficiently obtain a collection of edge flip of flip operators such that these flip operators are just edge flips. That is, if you sort of allow mutating the basis of detecting regions that you're considering along the way. And now it turns out that every gadget that we can consider on the diagram is spacetime equivalent to something that's built from flip operators and something that acts on the boundary. So for a running example, for this instantiation, we can use flip operators to collect all the faults that are stuck in the same detecting region. In our running example, we only have one detecting region, so we can transform all gadgets using spacetime equivalence to sort of all be stuck on this one single edge over here. And then since these Pauli boxes have their sort of Clifford decomposition using the Clifford conjugation, we can compress all of the boxes into one. And this is you can like this is a valid diagrammatic operation. You can also just view this as syntactic sugar for this diagram. And the key thing about this sort of using flip operators is that once we have collected all of these stuck fault gadgets on one edge, we can disconnect the flip operators. And this will yield us a diagram that just suddenly has a full separation between the base diagram and the description of the noise model. So for each flip operator, in our case just one, we would obtain one free-floating green spider that connects to all the fault gadgets that use this flip operator in the previous representation. And so we now see that all of the fault edges that we can consider, so all of the edges where faults happen, all of the noise is inside the fault gadgets, and these fault gadgets are on the boundary of the diagram. And now, as I said in the beginning, we can normalize and uniquify both parts individually. And this, well, this concludes the first stage, and this moves us to the second stage of sort of uniquifying these both parts. And we're going to focus on just the second part, just the noise description of the diagram. So since we only care about undetectable faults in fault equivalence, we're going to try to get rid of all the detectable faults. And we're going to recall that if we have two faults that flip the same detecting region, we can combine them to some combination which doesn't flip this detecting region anymore. Now, we can insert this combination into the noise model and actually thus change the set of atomic faults in the noise model to also contain this combination. And we're going to insert it with the value of the atomic weight sum of the original faults. And this turns out to not change this noise model N in like a too relevant way, since the sort of amended noise model is still fault equivalent to the old one. In other terms, if we add this combination as an atomic fault to the noise model, we do not actually get any new undetectable classes, since we were able to generate it before. And also the minimum weight of each equivalence class doesn't change, since we're introducing it just with its weight sum that was used by the inductive weight previously as well. So the idea to get rid of all the detectable faults is that if we pick any fault F that flips the detecting region, and we now introduce all combinations with all the other faults that flip the same detecting region, then now suddenly this fault F is obsolete in the noise model. We can sort of reason through this by stating that, well, if we have any undetectable fault that's relevant to fault equivalence, if we have any undetectable fault that uses f to be generated in one of its decompositions, then in order to be undetectable, it must flip that detecting region back. And so it must involve at least one other fault that also flips the detecting region. So instead of using these two individually, we can also just use their combination. We can compress this into one new rule, and that's indeed one of the axioms that we introduce, where if you have one fault that occurs with weight W1, and you have a bunch, and this fault and a bunch of other faults are connected to the same free-floating spider that represents the detecting region, then you can introduce the combination of this fault with all other faults, and just be left with all the other faults being connected to the detection region. So W1 is removed from the new noise model, but at the cost of introducing all these combinations. And this is sort of focused on just like the head region of fault gadgets, and we can use it to derive a bigger rule that applies to arbitrary fault gadgets with arbitrary Pauli boxes. So this rule allows us to, given any fault that flips any detecting region, remove it from the noise model. We can iterate this until there are no more faults in the noise model that flip any detecting regions. So all atomic faults in the noise model are now undetectable. In our running example, this would look like the following. So we first consider just the leftmost fault here that is connected to this free-floating spider. So it flips the detecting, it flips the sign of the detecting region. And then we introduce its combinations. And since there are three other faults, we introduce three fault gadgets. And then we take the next one, we introduce two new fault gadgets. Then we take the next one, and there's only one remaining, so we introduce one fault gadget. And then for the last one, there are no other fault gadgets to combine it with, so we can just remove it immediately. You may realize that especially in cases where you have many interconnected detecting regions that interact, this can become intractable really, really fast. But since this is just a theoretic guarantee, we aren't concerned with that right now. So this is step one done. We now have a noise model with just undetectable faults. The second thing we're trying to do is enumerating all of the equivalence classes that can happen in a noise model. So generating all equivalence classes. In other words, we're trying to ensure that each equivalence class has at least one member of it present in the diagram itself, in the thing that describes a noise model. We're going to use it, use a new rule that we introduce additionally as an axiom. And this rule basically states that if you have two faults, then you can just introduce a combination with their weight sum. This is similar to the one for detectable faults, but it just operates on undetectable faults, and in particular, it doesn't require two things to be connected to the same detecting region. And again, we can use this rule to derive a bigger rule. So the strategy to generate all equivalence classes is to, well, basically just generate them, to just form all combinations of undetectable faults. And this sort of by construction guarantees that every generated class that is possible in a noise model is already present with some member somewhere. And again, this will also become really intractable really fast. As a side fact, fault equivalence is NP hard to check. So we may expect this to get like really, really sort of computationally intensive would we want to implement this. Now, after the second step, we have all equivalence classes of our noise model with perhaps many, many, many instances, different instances of members. And now what we would want to do is to reduce all of those members in the equivalence classes to just one canonical one. And ideally, it would carry the minimum weight, since the minimum weight of this equivalence class, since that's kind of what we care about, this minimum induced weight for each equivalence class, to be able to determine whether something is fault equivalent or not. So the goal here is to remove all but one representative from each class. And if we recall that we have defined spacetime equivalence to be something that relates to faults when they have some inconsequential fault connecting them. And we have a rule, the stabilize introduction rule, that allows us to introduce inconsequential faults. So using this fault gadget transformation that we derive from this stabilize introduction rule, we can make all fault gadgets that represent faults in the same class, just make them look the same. And we can just choose an arbitrary canonical representative per class. You could choose the lexicographically smallest one, you could choose a random one. As long as it's fixed, it's fine. So we again need something to reduce two fault gadgets. Like now they look all the same. Now we want to like sort of merge them all together. We're going to use yet another axiom. This is the bigger rule that's derived from the axiom, and we use the axiom exactly here. And it's saying that if we have two fault gadgets that represent the same fault, we can merge them and take the minimum of their weight. And suddenly, if we do this for all of the members of each class, then we receive exactly one member per class that's annotated with the minimum weight of the faults in this class. And so we're almost there. And it turns out that this noise model part, where we removed all the detectable faults by unfolding and then generated all the equivalence classes and then collapsed them again to have one member per class, but each class is present. This noise model part is unique up to reordering of these fault gadgets. So up to reordering of the sort of single members of equivalence classes. We can now just reorder them in some canonical way. We could again choose lexicographical ordering. We can also use this sort of compressed notation that we encountered during the flip operators to achieve the uniqueness, since then ordering doesn't matter anymore. And this is already the normal form that we need for this noise model part. This is unique now. For the base diagram, we can just borrow another unique form. In this case, we would use the reduced AP form for this diagram, and we know that we can bring this base diagram, this fault-free base diagram, into this form since we're only using the fault-free Clifford rules in that case, and we know that those are complete by another result. Now, we have two unique diagrams that compose to another unique diagram. And this means that we have now just obtained a unique diagram per fault equivalence class, which is the thing that we wanted in the first place. So this is, for example, how the sort of unique form, the completely normalized form of the running example would look like. You have the base diagram that's in the reduced AP form over here, and then you have the noise model description on the boundary. Now, the rules that we used are sound, or at least you trusted me that they are sound. And so the new diagram is fault equivalent to the original one. And since both diagrams on the fault equivalence, both diagrams on the left-hand side and right-hand side of the fault equivalence that we were trying to get some derivation for, if we do this for the other one, they should just meet up, sort of just like this. And if we look at the rewrite, then this is indeed what we can show. We can show that the left-hand side with the first diagram with the first noise model and the second diagram with the second noise model, you can they are fault equivalent both to this same unique reduced AP with a normalized noise model form. And that, in essence, is completeness. So now that that's done, now that that's proven, you may ask what's coming. Since the proof is constructive, like this whole procedure was coming up with ways and algorithms to actually do this, we can implement this. And this already sparked a new open source project called Parity. And the algorithms implemented there, especially for finding Pauli webs and for checking fault equivalence, so iterating on those equivalence classes, they need optimization and generalization. So that's where it's headed right now. And we can also integrate this with other tools. So if we, I mean, we're now at the end, but if you slightly recall the form that our diagram had at the end of stage 1, where we completely separated the noise model description from the base diagram, then it turns out that this noise model description actually forms a tenor graph of the noise model in the sense that STIM, for example, would have a DEM or a tenor graph. And then we can integrate this with other tools like STIM to, for example, generate decoders from that. Currently, this construction would probably require modifications to be able to be generalized beyond the Clifford diagrams and just Pauli noise. So that is one other direction of future work, trying to not only do this for Clifford diagrams, but for example, some restricted version of some approximately general set. And one question we may ask is if we can use approximations like Pauli twirling to like approximate more general noise models than just Pauli noise. This is just an idea. I don't know if this is headed somewhere. And finally, the focus on this talk was on the weighted noise, since this like sort of interaction between two weight values, taking this minimum and adding them, is really simple. However, like we only needed this interaction between two values or these two annotations of fault gadgets in stage 2. Up to the end of stage 1, we only ever cared about the Pauli boxes that are attached to the fault gadgets. So we can do this whole extraction without caring about the weight annotations. They can be variables, they can be expressions, they can be anything. And then we only need to define for this very limited set of operations in stage 2, what is the interaction between two values attached to fault gadgets? And in this way, we would be able to generalize this result of completeness to more general noise. Yeah, so the question is, can we apply this to more general noise models, and what restrictions would we have to put on these more general noise models or on the rules that we apply to them to be able to implement this completeness result? And yeah, this concludes my talk, and I thank you for listening.
Thank you, Max. So if you have questions, feel free to unmute yourself.
Hey, joining from the train here, so sorry if the sound is unclear or the video is blurry. I had one question. Because your result, if I sort of view it as like what category beneath it is you have your Clifford diagrams, and then they have associated to each edge well, they have like a set of subsets of the edges, which each have a number associated to them, and then you're rewriting between those two types of objects. But suppose I'm interested in the fragment of just a simple edge noise models.
Yeah.
Like suppose I have a diagram D1, which is the simple edge model, and diagram D2, which is the simple edge model. And I want to keep doing rewrites that stay in this fragment of the simple edge noise fits. Like if I understand correctly, your proof does not do that, right? Because you need to go to these weighted errors.
So one thing that fault gadgets allow you to do is already just reduce the things you need to consider from all general Pauli products to just these Z edge flips. And then another thing you can show is that you don't even need to have more general weight. You can only use weight 1. So by a little trick, a little rule you can derive, that if you have a fault gadget that's annotated with a weight W, then if you just repeat this sort of green spider W times and annotate each edge with 1, then you get the same thing. These are fault equivalent. So if you now define a fault-free edge to have a weight 1 Z fault, then you only need the distinction on diagram edges between a faulty edge and a fault-free edge. And suddenly you're able to describe all weighted Pauli noise models using this construction.
Okay, so then you essentially treat the weight W as a syntactic sugar for this other thing, and then you remain in the land where every edge just says weight 1 there.
Yeah. So using this rule, you can sort of like view this weight W as syntactic sugar for this expanded version. But handling this expanded version would just be very cumbersome in other rules. So for each for each instantiation of this sort of like these almost polymorphic-ish rules, you will have an actual representation of what this rule means in terms of just weight 1 edge flip noise. Yeah.
Thanks.
Clear? We cannot hear you if you are saying something.
Nope. I couldn't hear you either. Well, so maybe we'll let Leah to figure out the sound. I have a few questions.
Okay.
So when you talk about this tenor graph, like where you showed us earlier, I wonder if you could find a way to simplify your fault gadget such that you could track how fault propagates in the diagram. And maybe this will allow you to do, for example, fault-tolerant circuit synthesis, because now you know which part of the diagram is more faulty, or like what kinds of the fault is problematic. And then you can assign flag qubit to deal with these problematic faults. Like, are you able to kind of track faults more like conveniently using the simplified version of fault gadgets?
So so if we just look at the here, all of the equivalent faults, all of the faults that would propagate throughout the diagram, in this form are already like collapsed to one, or could be collapsed to one single instance. So it's already all pushed out. You could, on each fault gadget, annotate sort of where it's coming from, and then since you have an easy way of determining which faults are detectable and which faults aren't, you know, you can sort of derive something that tells you where to insert flag qubits. But since usually you not only want to consider post-selected versions, but also versions with a decoder, where you have some sort of more complicated interaction between detectable faults. If you recall, these are only the atomic ones. These are not the all generated ones. And if this interaction becomes more complicated, then it's still hard to derive what your like sort of problematic or most problematic errors are from this representation. So this is, if you recall a STIM detector error model, that's like a list of the independent error mechanisms that flip or violate detectors. This is exactly equivalent to that description.
And is this process like knowing what kinds of flag qubit you should assign efficient, or this is combinatorial analysis?
This is, I'm even unsure whether it's what sort of analysis it is, but I'm quite sure it's not efficient.
No, it's not, like, right? Maybe for weight 1 faults it might be efficient because you can just look at them. You also have to worry about weight, like combinations of 2 faults or 3 faults that propagate out to like weight 5 or something. And at that point, you're back to the computationally hard problem. But more generally, I'm not sure. Yeah, I mean, yeah, you can kind of do it via this. Yeah, you could definitely do it at this stage, but like it is computationally hard.
One problem that you have, for example, is that the difference you have the difference between the atomic weight, which is the one that you sort of visualize here, and the induced weight. Since you might have a cheaper construction that is way more detrimental to you using some other atomic faults that are not this atomic fault. Leah, have you reviewed your sound?
Yeah, I think it works now.
Yes, it does.
Thank goodness. Gosh. Okay. I have 2 questions. I'll start with the shorter one. The shorter one is, how would you recommend to go about like kind of hacking away at correlated edge noises? So like 2-qubit faults where they're not the probabilities are more likely for some Pauli strings versus others. Is there a gadget that can be inserted there, or just like it's not clear? Well, it's definitely an extension, but how would you deal with it?
It is an extension, and I think that like these gadgets are very inherently independent from each other. So what you could do is for correlated errors, add 2 sort of independent gadgets and push them outside up to this like end of the first stage, while you're in like a more general way or meta way, remember that they're correlated somehow. Like this whole first stage was a transformation from fault gadgets where you can track each fault gadget to one outside. I'm unsure as to what the exact interaction between fault gadgets is in the second stage. And I don't think you can, like, using this framework, faithfully represent correlated faults on diagrams. But if you remember it in a sort of meta way, then that's easily possible.
Sorry, Max, I might have misunderstood the use of fault gadget because I remembered in the fault tolerance by construction paper, you did introduce like IXYZ, which is a fault, and then that happens simultaneously, and you're able to use a fault gadget to represent it. Now,
Yes.
if you make this IXYZ as IXX, then isn't that corresponding to a coherent fault where, like they are simultaneously happening? And then you can have fault gadget representation for it.
Well, it's the error mechanism that a fault gadget represents is a thing that's either turned on or turned off. So for any given sample of the diagram, I sample one probability, and it tells me whether this fault should be included in the sample that I'm considering or not. For correlated noise, you will sample one thing, and then depending on the outcome of that thing, sample another thing. So this isn't necessarily anything that's faithfully representable by fault gadgets.
But you can say you have a highly entangled fault that appears independently to other faults with some high probability. So that indeed, Sarah, what you're saying is one way to look at it. But like if you have more complex noise models, then stuff starts becoming very difficult.
Thank you.
I think, Leah, you had a second question?
Yeah, I did. Sorry, John. I have a meeting in a few minutes. So your proof of the completeness normal form is AP normal form with a noise channel after for states. And so that's really useful for fault-tolerant state preparation, but I'm not sure how to interpret it for maps. So things that are not states that might have inputs and outputs. Because after the normal form, then your noise channel kind of goes both before and after. How does this come up with a physically useful or interpretable construction, or would you call it that you're kind of initiating some redundant info in an in silico block?
So the whole consideration of putting this into a state just follows the like usual isomorphism that you can consider each linear map as a state. So down here, I just draw this noise model on the edges to sort of make it more easily visualizable what the transformation from the last diagram was. I'm unsure whether I understood the second part of your question.
I meant that because if you're having a map instead, say you take the choice state of that, and then you do a normal form like this. When you unchoy it, then you end up with the normal form touches that diagram touches both the inputs and outputs, and
Yes.
so it's not it's not a physically interpretable construction. Or I guess you can physically interpret it, but that would be as some ancilla information that you have to possibly remain idealized. I'm not sure.
So the whole notion of idealized edges is something that we cannot interpret physically. Like we cannot just tell a quantum computer to not have a fault on this edge. And so this like in anything that uses idealized edges, you would to be able to interpret it effectively, you would need to extract some circuit that is fault equivalent to that idealized version that contains no idealized edges. So if you just undo this sort of isomorphism and have the linear map again, then you get a thing that's like sort of that may be implementable physically, but isn't yet really something that you can just implement.
Okay. Yeah, I suspect what you get is the noise channel. So like a channel, a supermap, or not. I don't know if it's super. Well, it's a it's a higher order map that takes your idealized map to the one with the before and after subdiagram.
Yeah, well, it is definitely a noise channel, but like with the semantic effect of the diagram baked in. This diagram in AP forms encodes the semantic effect of the original diagram. So if you now undo this sort of state isomorphism, then suddenly you have, as you said, the noise model on both sides, and in the middle is semantic diagram. So in a way, you have some deterministic part, or not, it doesn't need to be deterministic, but some like noise-free part in the middle that changes, that sort of encodes a base version of your channel. And then you have some noisy part of the channel. And what we have done is we've separated those two. But I don't know if you can go any further in interpreting this.
I think you can get a normal form for the isometry case because you can take the talk I gave at the seminar in June was to take the reduced AP normal form and then convert it to an isometry normal form. So I suspect you can also, there will be some equivalent normal form for the isometry case. I think it's some kind of channel, but well, we can discuss this, but
This would be interesting to look at.
it's really interesting. Yeah. Yeah, I suspect this is some kind of normal form that that can be written down. Thanks.
Right. John.
Right. Yeah, so one thing that's always nice about completeness is you sort of get to identify what the necessary components are for like proving everything essentially, right? So you have these new fault equivalent rewrites that you introduced. So I'm wondering how much are these formalizations of things that people already knew about sort of fault equivalence or errors, sort of saying like, oh, these errors should commute to something, versus which rules might contain new insights, like, oh, here we're saying something that's really non-trivial about faults.
So one result that was that related to things in a way that at least we haven't encountered before is if you have two no, not if you have two, but if you have the group of inconsequential faults, then this is exactly equal to the group of the group of faults generated by these local spider stabilizers. So the Pauli webs in essence. This is something like that's we haven't found a like sort of trivial proof for. But we have found a proof, and we haven't encountered this result. So that's a new statement, but that's only one of the like intermediate statements, and isn't really something that's unique to this completeness result, in terms of applications. The remaining stuff, so for example, this notion of generally pushing out and ignoring phases, like the details of how we ignore phases, for example, this is something that I think is unique, and this way of thinking about fault equivalence in terms of these equivalence classes, or almost in terms of flip Pauli webs. This is something that's new to this work, but all these ways of pushing around faults, this was already done, for example, in tools like STIM. So as I said, we have this detector error model at the end of stage 1, which is not really a coincidence, but just sort of shows how STIM does it, and how this is sort of a good way to obtain it in a diagrammatic way. And yeah, considering all undetectable faults, I think that's just combinatorics. There's nothing really, like, wagering to say this is nothing really innovative here. But yeah, up to the end of the first stage, there were some new results, some old ones. The general notion of pushing outside, that we need to push outside to be able to obtain something, this was already present.
All right, then another question. So one really nice thing about the Clifford completeness proof with the AP form is that for a large part of the proof, you can essentially just apply the simplifying rewrites of the block computation, pivoting, just anywhere it sort of matches in the diagram. And it's only at the last stage, when you have your AP form, you have to go to reduce the AP form. Then you have to be careful about the order in which you apply rewrites. I was wondering in how much your proof, like for how long you can sort of do this thing. I'm just going to apply some rewrite somewhere. I'm going to make progress, versus having to do it in like a very directed manner for like almost the entire procedure.
So you're saying how much of this proof is local versus how much of it operates globally?
Yeah. I guess that's
okay. So the it kind of depends on how large you put the local scope. So if you just look at each fault gadget individually, then or at pairs of fault gadgets as most, then all the way, like I think the entire proof can stay local. And then only up to when you need like, well, it depends on if you want to consider we need to combine with all other faults that exist to generate all equivalence classes. If you consider that a global one, but each operation that you do is only local. But this is possible for weights. If you now use, for example, if you generalize to stochastic noise, then we haven't yet solved this, but one thing that we found is that probably you will need to have some notion of if you change the probability on one gadget, then you will need to balance out the probabilities on other gadgets as well, depending up to some notion of how to find them and how to update this in order for the whole thing to stay a valid probability distribution. So yeah, these sort of like non-local interactions between fault gadgets we haven't found them to be present with weights, but for more general things they might be.
right. Thanks.
So my question is actually related to John's question. So I was looking at figure 3 of your paper, which is the complete set of rewrite rules. And so it seems that for the top layer, you're talking about the Clifford rewrite rules, which comes from the normal form that you already have.
Wait, let me pull those up here. There we go.
Right. So is the second part, which is a basic fault handling,
Yes.
basically how you push Pauli across Clifford gate? Like
Yeah,
how
like those are the rules that we need for the first stage. Only those three are all that we need. So the first one is saying that, well, if you have some identity ZX diagram, then ignoring the Pauli's on one half of the diagram kind of does nothing, and you can just like take the whole thing as faulty. And then the next one is saying that, well, if you have any you can view a phase annotation on the red spider of a fault gadget as something that encodes the phase that you would obtain when you activate this fault gadget. So when you introduce a fault, then in order to sort of obtain the same fault gadget, you will need to introduce some global phase according to this k pi over 2. And the same thing happens if you have this green pi over 2 between two fault gadgets.
but I couldn't
yeah.
see the global phase in the right-hand side of the diagram.
So this fault equivalence is up to global phase, but you could write it in terms of an expression of k.
Mm.
You can also represent it as a scalar. In the I think that the proof is somewhere in the completeness paper as well. But you can prove that these two things are fault equivalent basically by popping out this red pi over 2 with an idealized edge, like having an sort of zero phase red spider and then having this one dangling, and using the copy rule to sort of squash away the phase.
Right.
And having it as a free floating scalar. And then since we ignore things up to scalar, we just remove it.
Mm-hmm.
Well, up to a non-zero scalar, and this one is non-zero.
Right. And if you consider a different notion of fault equivalence, which is distance non-decreasing, how would you expect this rewrite rule set change?
You're saying so.
So if you transform the diagram, but it's not bidirectional, it's only one directional.
I am unsure whether it's in that version of the completeness paper, but it's at least in the thesis which that paper is based on. We show that there are more restrictions to fault equivalence. One is that you only consider fault equivalence up to some weight. So this is only like it's only valid for up to some operators for up to some weight. Or it's only one directional. And for each of those cases individually, you have to just add one more rule to obtain a completeness result for this new relation that you're forming. And if you want both modifications, if you want to have something that is unidirectional, we call this fault boundedness. If you want to have something that's unidirectional and restricted in weight, so it's only valid up to some weight W, then you just add both rules and you suddenly obtain a complete set for this new relation. So you will still need all of these rules, but since like basically you're doing full fault equivalence up to the point where you need to change something, and then you use one last rule to change the last thing that you need to change. Yeah.
So Max, is that because you can in both those cases you can just like use your algorithm to go to the normal form, and then you just have one rule that says, okay, and now all weights above a certain weight, just cancel off and get rid of them, and then you're done. Get the normal form like up to this W weight.
So
and within non-decreasing, so then you go to the normal form, and then you sort of identify, oh, this is now a coarse graining of this other moisture.
this is exactly what's happening. Yeah.
Okay, yeah, that makes sense. Yeah.
Cool. And I also have a question about this restricted fragment of ZX diagrams. So we know that C naught plus dihedral are also like not universal. So my guess is if you think of generalizing completeness to a universal ZX calculus, that's probably hard. But if you think of generalizing it to a different like taste of Clifford, maybe it's easy. Like I wonder what stopped you from generalizing it to other fragments.
It depends on what you define as hard and what you define as easy. The second stage of this was already hard in the Clifford fragment. Like we already had exponential explosions using these like detectable fault unfolding and the generating all undetectable equivalence classes. And so the only thing that might switch between hard and easy is the first stage. In terms of what's stopping us, the Clifford fragment gives you a nice representation, a nice well-known representation, just using like Pauli transformations or stabilizers in that sense. So this whole trick of which Pauli webs do faults anti-commute with to efficiently determine whether two faults are spacetime equivalent, you would need to come up with like a similar thing to be able to pull off a similar trick in this new fragment. So I don't know whether your proposed fragment sort of allows for such a thing, but you will have to come up with alternatives to that.
I want to add to that sinodihedral is only a non-universal fragment if you restrict unitaries. Once you have an as opposed selection, which in a select diagram you should have, then it is exactly as powerful as universal. So that doesn't really get you anything easier.
Oh, I see. Okay. I was thinking about only have like phase-free X and Z spiders with like arbitrary Z rotation. And okay, I didn't know it could be that complicated. Okay, thank you.
One thing you may consider is that if you have some more complicated gate, like a T gate, then what you do after so what you do is you track more complicated faults and you try to approximate them using other like sort of independent error mechanisms. So in the middle of pushing out, you try to already adjust your atomic fault set such that the probability distribution, like the overall probability distribution that you try to get at the end, will stay roughly the same, or like the closest you can get with independent error mechanisms. But I don't know whether that's efficient to obtain, or in any way like close enough to be useful, to be able to obtain some detector error model adjacent thing for Clifford plus T.
Thank you. Do we have any last minute questions for Max? So Max, I have one last question for you. Have you thought about thinking with respect to Clifford noise, using your method? Like, because I know that when we're thinking about Pauli web, we're thinking about how Pauli is propagated, but what if we could because for example, the XP code, they're thinking about like fighting against the Clifford noise. So far, I don't see any ZX representation of this kind of codes or the corresponding noise model.
I'm not too familiar with Clifford noise, but I imagine that you could at least represent it in the diagram using a fault gadget where the target is not a Pauli box, but some Clifford. I'm unsure how you would need to update the like sort of pushing like these transformation rules. How these would map. Perhaps you would like here we had one rule that was responsible for us being able to push or transform fault gadgets through arbitrary diagrams just using these inconsequential faults. With the Cliffords, you may have to come up with something that's more special to specific contexts in which you can derive this. So this might only be possible for the subset of diagrams where you can apply these rules. But yeah, it would be, well, perhaps you will be able to use Pauli web, since all Cliffords do is transform Paulis into other Paulis. So you should be able to use. I think you should be able to use Pauli webs in a similar manner. This sounds possible, but I'm not sure.
Yeah, because I was wondering during your stage 1, you were thinking about how do you push the fault gadget to the left end of the circuit and the right end of or like the left end of the diagram, right end of the diagram. Now we know ZX calculus is complete. This means you can have rewire rules to transform the diagram, but I'm just not sure how would you do it efficiently.
Yeah. Yeah, that's that. I mean, this efficiency is one major advantage of thinking about them in terms of Pauli webs. And yeah, as I said, I think you can generalize this in some way. We have thought about it, or begun to thought about QDITs, cases of QDITs, where you do a similar thing to consider these targets of fault gadgets to be not just Pauli boxes, but some more arbitrary thing that just maps something to like a Pauli web to something, some other Pauli web. And in a sense, I think you can, if you recall the Pauli boxes, they were just some Clifford conjugation of a green spider.
Yeah.
Using very specific Cliffords. This should easily generalize to just arbitrary Cliffords. You can just put any Clifford diagram as long as you also obtain the adjoint. Just put both of these around the green spider, and suddenly you have a new target, which, as Cliffords map this, like map Pauli webs to other Pauli webs, it should form a valid fault gadget.
Let me just drop in, because with the XP codes and the Clifford noise that Sarah was talking about, I talked about to someone at the Dutch tool, and yeah, if you get Clifford noise, you need controlled Cliffords to represent them, like the generalization of Pauli boxes. So you get like H boxes in your diagram, and not just pure ZX diagrams anymore. The representation of arbitrary XP codes, like we try to build it, and it's very, very complicated. So I think this would, in general, be like quite a difficult research project that would not follow easily at all from your current results. Like it should then be something like, okay, we simplify a phase-free ZH diagram, something like that. But that might be the next target.
Yeah, but that's definitely an interesting thing to look at, is how can we generalize the noise that we can apply this to.
Sorry, John, why you would mention simplifying the phase-free ZX diagram?
ZH diagram.
Oh, ZH diagram. Oh, okay. So you probably need other fragments of ZX diagrams that require other generators than just the Z and X spiders.
Well, if you want Clifford noise, you need controlled Cliffords. So then you need H boxes.
That does make sense. Yes. Yeah, as long as you can have some sort of analogy of these Pauli boxes, then it should work out.
That might also get you the way to having T gates in your fragment, because if you push an X to a T, you get an S. So what you really want is like an S noise, and the way you can represent this is like a controlled S gate, where the control is sort of your fault gadget.